Hello all, welcome back to my YouTube channel all about VLSI. In this particular video, we are going to discuss about PCIe. In our previous videos, we have discussed about ISA, EISA, and we have also discussed about the disadvantages we were having in ISA, and we have discussed about the advantages and why we have moved from ISA to PCI. We have discussed and what were the disadvantages in PCI and why are we moving to PCIe is what we are going to discuss in our in our today's session, right? So if you haven't watched the previous session, I recommend you to watch the previous recording so that you will have exact idea about what we are discussing about, right? Now, basically, PCI was a parallel bus architecture and PCIe is a serial bus architecture. And we are going to discuss what is the reason we are going to shift from PCI to PCIe. Now, so what are we going to cover is we are going to learn why we have shifted from PCI and PCIX and why we have moved to PCIe and why we have converted a parallel bus architecture into a serial architecture, like why we are preferring a serial bus compared to a parallel bus, and what exactly we are solving in PCIe, like clock skew. It may be a crosstalk, or it may be ISA, or it may be solving the problem of stubs and reflections that we are going to discuss in the case of our PCIe. And we are going to discuss all the particular limitations which we were having in in the case of my parallel bus that we are going to solve in my serial bus architecture. That is what we are going to discuss in the case of our this particular session, right? Now, so first of all, let us see how the PCI SIG was in by 2001. So SIG is nothing but special interest group. So basically, PCI X 2.0 was being finalized, and they were basically trying to push the parallel bus architecture to 533 megahertz by using a concept which is known as quad data rate signaling. That means for every particular transfer or every particular cycle, they are going to send basically four bits of data. So that is nothing but my QDR. Now, so that is what squeezing four data transfers out of every particular clock edge, and they are trying to increase the pace using the parallel bus architecture. Now, PCI begin basically PCI. We have discussed that the very basic PCI was 33 megahertz with working with a single data rate, where that means one transfer per clock, and which was comfortable with a physical limit of shared parallel bus, and PCI X, which was pushed to 133 megahertz. And first, they have used double and then quad data rate for just increasing the speed of operation and bandwidth. Now, but without redesigning the bus topology, so they haven't redesigned the bus topology, and they have tried to increase the bandwidth and all. But this particular tricks haven't been not satisfying, and they were introducing more and more limitations like clock skew and crosstalk and stub reflection problems. These were very dominant while we were trying to increase the speed of operation and bandwidth. Now, so that particular problems was resolved by our PCIe, that is nothing but PCI. So already the industry was moving to serial communication. I mean serial bus architecture. If you see in your networking, where gigabit Ethernet was using differential serial signaling for moving well beyond what parallel copper links could reliably achieve. So in the case of our networking, we have discussed about Ethernet protocol also. There also we were using the serial bus interface, and in storaging also, and in processor interconnects. So everything, the industry was slowly moving towards serial. So PCI was also trying to move towards serial from the parallel. So this was basically Intel's response to the 3G IO timeline, where in 1999, one group work formed where they have begun exploring a next generation interconnect to succeed PCI and PCIX. And in 1999 to 2000, 3G IO evolved, and this particular effort to matures the third generation initiative with a radical founding premise. And in 2001, Intel has contributed to PCI Special Interest Group, and next in July 2002, a standard PCI Express 1.0 was formed. Right now, so coming to the main question, why would you replace a 32-bit or a 64-bit wide parallel bus with a serial link that sends only one bit at a time? Isn't wider always faster? Because we do have this particular kind of doubt, like parallel data or parallel bus will have the faster data rate. Why are we choosing a serial particular bus? So this answer will be given by physics. Let's see what is that we are going to have. Now, what problems that our serial point interface is trying to escape us from the parallel bus interface, which was introduced by parallel bus interface. Let's try to understand. So basically, in our PCI, before when we were using PCI, we were having n wires for n bits of data. For transferring n bits of data, I was having n wires. That means one bit of data was sent through a single dedicated wire, and all those particular are synchronized to a shared, separately distributed clock, and all bits must arrive at the receiver simultaneously. This was the case in the case of my PCI, and the clock was given by the central unit to all the particular wires. All the particular wires which were sending the data are synchronized to my clock. Now, in PCIe architecture, we are not going to have n wires for n bits of data. No, not at all. We are going to have a small number of wires, as few as two wires, one for direction and for one for sending the data. So bits sent one after the another at very high speed. So instead of having dedicated wires for dedicated number of bits, only one particular wire is dedicated, and all the bits are sent serially one by one at a very higher speeds using only a single wire. And the clock is not given by a particular central unit, as in the case of my PCA. The clock is also embedded into my data stream, and it is not distributed separately. So this is the difference between PCI architecture and PCIe architecture. So this single architectural shift is trying to eliminate or fundamentally change every physical problem caused by parallel bus. Let us try to understand what are those physical problems in great detail. So the first physical problem was clock skew. So basically, PCI distributes one shared clock. So in the case of our PCI protocol, we have seen that we are going to have one shared clock given to all the particular devices on the particular bus, and PCB traces have a finite length, and they are going to propagate the signals at a finite speed, around 15 to 18 centimeters per nanosecond in FB4 fiberglass PCB material. The clock is going to reach a nearby device slightly before it reaches farther one. For example, if I'm going to have one PC architecture where I have device 1 over here and device 2 farther away from the clock source, right? So due to this particular architecture, what is happening? The device 1 is going to get the clock faster compared to my device 2. So due to this particular case of PCB tracing, I'm going to have I'm basically introducing clock skew. Now, for example, let's take a example, like let's say suppose if I have a motherboard where PCA bus spans 25 centimeters from chipset to farther slot. So a propagation delay of 17 centimeter per nanosecond introduces a roughly 1.5 nanoseconds of skew between the nearest device, that is D1, and farthest device, which is D2, and a meaningful byte out a already short clock period. So this is the reason we are going to get clock skew. And how PCI is going to solve this particular issue of clock skewing? First of all, we are not going to have a distributed clock given to all devices in the case of my PCIe. I'm going to have a clock embedded into my data bus itself. So in our Ethernet protocol also we have seen we were basically embedding the clock, right? So here also we are going to do the same thing. We are not going to have a separate clock line. PCIe is not going to send a separate clock signal alongside with the data. So PCI is going to share that particular clock line, but in the case of my PCI, I'm not going to have. So in the receiver, it is going to have something known as clock data recovery circuit. So within the data itself, we are going to send the clock, and whoever which is receiving the data, they are going to basically recover the clock from the data itself. Okay, let's say suppose if this is my device, which is basically receiving the data from a particular PCIe bus, which is basically receiving a data from PCIe bus. So there is no separate clock which is basically sent to this particular receiver device, and they're not synchronized with each other. No. So a particular within the data itself, a clock signal will also be sent into this particular bus, and the receiver who is receiving this particular data along with this clock, it is going to recover the clock using clock data recovery circuits. And here skew is not an issue at all, because there is no clock derived from the same physical wire, and since the clock is derived from the same physical wire, and there is no shade clock or there is no distributed clock, there is no problem of skew arises also. Okay. And one more thing is encoding. So basically, whatever the data which was sent via this particular PCIe bus was encoded as 8-bit or 10-bit in generation 1 and generation 2, and 128-bit or 130-bit in generation 3 plus, specifically to guarantee frequent transitions so that our clock data recovery circuit can continuously track the correct sampling point. Okay. So if you are not aware about what do you mean by clock data recovery circuit, once go through the clock data recovery circuit briefly so that you will come to know what exactly how it is working and how encoding basically helps in recovering the clock. That is very, very important, right? And we are not going to have lane to lane skew. So basically each lane is going to have self clocks independently, and residual skew across a multi-lane link is handled separately via lane to lane or d-skew using skp orders, right? So this is how we are basically going to solve the clock skew. And next is the next problem over here is crosstalk. So let's try to understand why a crosstalk is going to happen on a parallel bus. See, basically PCI is going to have 32 or 64 address or data traces side by side on the PCB. And basically, if there is any change in voltage on one particular trace, it induces an unwanted voltage on its another neighboring victim through an electromagnetic coupling, where we are going to govern by two mechanisms working together. For example, if I'm going to have two buses parallelly, then if there is any particular unused unwanted voltage is present, if there is any changing voltage on this particular track, it is going to induce then unwanted voltage on the other track. This was the issue which was happening if we were having parallel traces, right? So basically it is known as capacitive coupling. So we are going to have a problem which is known as capacitive coupling, which is basically a changing voltage on the aggressor injects current into the victim trace through parasitic capacitance. Suppose if there is a changing voltage in this particular lane 1, that will basically injects current into the lane 2. This is known as capacitive coupling, and this is a problem which was existing when we were having parallel traces. And inductive coupling. So if there is any changing current on the aggressor, that means in the lane 1, that basically induces a voltage on the victim, that is my lane 2, and this is known as inductive coupling. So there was a problem of capacitive coupling and inductive coupling when we were working with parallel buses. So this is one of the best example. Then what we are going to do, how we are going to solve is we are going to use differential signals. So what do you mean by differential signals? So in our PCIe, we are going to use two wires. One is D plus and another is D minus. So whereas D plus is going, where these two wires are going to carry the same signal but flipped in the sign. For example, D plus is going to carry plus V. Example, if the data is 1 bit, we are going to allocate plus zero point 0.4 voltage to this particular bit, and if the bit is 0, we are going to allocate minus zero point 0.4 voltage. Okay. So let's say this is my lane 1 and it is D plus lane. Okay. So if I want to send 1 bit, I'm going to send zero point 0.4 voltage, or if I want to send 0, I'm going to use minus zero point 0.4 voltage. And I'm going to have one more lane which is D2. This is lane D2, where exactly opposite polarity I'm going to use on this particular lane. That means if I want to send bit 1, I'm going to send minus zero point 0.4 volts, and if I want to send 0 bit 0, I'm going to send plus zero point 0.4 volts. So our receiver, it is not going to measure D plus or D minus alone, but it is going to measure D plus and D minus collectively. So how it is going to measure? Let's say suppose if this particular lanes are connected to one of the receiver like this. If these two lanes are connected to the receiver, so receiver is going to collectively measure it. So what it is going to do? Let's say suppose D plus is getting plus zero point 0.4 volts and D minus it is getting minus zero point 0.4 volts. That means on the lane 1 we are going to get 1, and the lane 2 is also going to get 1, and in the lane 1, that is D plus, I'm going to get plus zero point 0.4 volts, and in the lane 2, I'm going to get minus zero point 0.4 volts. Okay. So what is happening? This particular receiver, it is going to add this two lanes, that is plus zero point 0.4 volts minus minus zero point 0.4 volts, which is nothing but zero point 0.8 volts. which is nothing but a clean one. Let's say suppose if I want to send a data 0, then what I'm going to do on the D plus line, I'm going to send minus 4 volt, minus 0.4 volts, and D minus line, I'm going to send plus zero point 0.4 volts. And if I'm going to subtract them, I'm going to get minus zero point 0.8 volts, which is a clean 0. So that means if I want to send a 1, then what I'm going to do on the D plus lane, I'm going to send plus zero point 0.4 volts, and on the D minus lane, I'm going to send minus zero point 0.4 volts, and the receiver, it is going to basically subtract them, so that I'm going to get zero point 0.8 volts. It is a clean one. And if I want to send 0 data, then on the D plus lane, I'm going to send minus zero point 0.4 volts, and the D minus lane, I'm going to send plus zero point 0.4 volts. And if I'm going to subtract them, I'm going to get minus zero point 0.8 volts, which is a clean 0. Now, let's say if there is a crosstalk which is being injected, and let's say we are going to use D plus and D minus. These are basically rooted right next to each other. They are basically twisted, and or you can say tightly coupled. And let's say if there is a noisy neighboring trace which is going to induce roughly the same extra voltage on both of them. Okay, so let's say to this particular two tightly coupled lanes, these are very close to each other, D plus and D minus. And let's say if there is a noisy neighbor which is present, and if it is going to induce the noise, then the noise will be induced on the both the lanes equally. Okay, so what is going to happen if, let's say, on the D plus lane, a zero point 0.1 volts was induced, so the voltage will be zero point 0.5 volts that will be having on our D plus lane. And D minus lane also, what I'm going to have plus zero point 0.0 volts I'm going to induce, and I'm going to have the voltage which is present is minus zero point 0.3 volts. If I'm going to subtract them, which is nothing but zero point 0.5 volts minus zero point 0.3 volts, which is zero point 0.8 volts only. So there is no particular noise. So noise is basically cancelled when I'm basically receiving the data. So this is how differential signaling is going to help me for eliminating the noise. And why this particular thing doesn't work on PCA? Because PCA traces are single ended, and each one is going to measure, each particular lane is going to be measured with respect to ground, not with respect to my other PCA trace. So that is the reason this particular differential signaling was not introduced in your PCA, and you were basically having crosstalk noise which is injected in our PCA. And that's the reason we are going to use this differential signaling in our PCIe. Now, other problem was stubs and reflections. Now, what is this particular reflection and why it is happening? So, see, in our PCA, we are going to have multiple devices connected with a particular. So, PCA multi-drop bus topology means every device connector is an impedance discontinuity. So we have seen that in PCA, we are going to have multiple devices which are connected like this. So let's say this is device 1, device 2, device 3, device 4, and it's a shared bus topology. And basically, each particular device is going to have the access to this particular bus. So due to this, what is going to happen? This particular devices are having different kind of impedances. So due to this impedance mismatch, our there may be reflections which are possible on this particular bus. So that's the reason we are not going to have in PCIe, we are not going to have a shared bus topology. We are going to have switched point to point topology to avoid this kind of reflections and impedance matching. So, so that is the reason we are basically trying to shift from serial that is the reason we are trying to shift from parallel bus architecture, which is shared bus architecture, to a serial point to point architecture for solving this kind of problems. So that's about this particular video. If you like this video, please like, share, and subscribe to my YouTube channel all about VLSI. Thank you.